Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome a speaker from Leipzig, Germany. And it will be about non-commutative coordinates from perturbative quantum gravity. So let us be perturbed by quantum gravity. It's all yours. Take it away.
Thank you very much.
Markus FRÖB, our speaker is Markus FRÖB. You taught me how to pronounce your name and I forgot to say it. Okay. I'm so sorry.
Right.
Yeah. Markus, we are happy to have you. It's all yours.
Thank you very much. Thank you for the invitation. I'm happy to be able to present to you these results. I was told that I can be interrupted at any time for questions, and I'm very happy about that. So please, anytime you don't understand anything, let me know. I started as a theoretical physicist working on quantum fields and curved spacetimes, perturbative quantum gravity. And then in the last maybe 6-7 years, became more mathematically rigorous, let me say. And so I hope I put the things on a level that you can understand. If not, if anything's unclear, then please ask me. So, now it works. Okay. First, I will give a short introduction to the topic and why I'm interested in it. Then I will explain to you how what the framework is in which I do all these computations, namely the algebraic approach to quantum fields and curved spacetimes, which was started by Haag, almost a century ago. Then in the third section, I'll tell about the concrete model, namely perturbative quantum gravity in that framework, and observables in that model, which are relational observables. I will explain what that is. And then finally, I will come to the non-commutative coordinates and the relation to non-commutative spacetimes, and of course end with a conclusion and output. So let's start with the introduction. What is the problem, or the physical problem? Well, we all know GR, general relativity, or in general, in the mathematical framework, differential geometry, describes spacetime as a classical level, as a manifold with a metric and differentiable structure. But this should break down, or is expected to break down at short distances. Namely, what will happen? Well, first of all, we know already in classical GR there are black holes. These are solutions of the theory with singularity at their center. So a point where quantities become infinite, so where the description of spacetime using GR or differential geometry can no longer be valid. And this is in fact a general thing that is expected in the theory, namely, well, there are various singularity theorems developed by Penrose and others, which tell us under certain reasonable physical conditions, at some time, in some regions of spacetime, black holes will form. And okay, so this is a problem. Our theory is not well defined there, so one has to go to find something else. And in fact, there is a further problem, namely, if one wants to do measurements, how one does this. Well, for example, looking through a telescope, that means there's light coming from somewhere, entering our telescopes, and we get a picture. If we want to have a closer look, we need to have light with higher intensity, shorter wavelengths, more energy. Or for example, at the LHC, big collider, where we shoot particles one against the other. So these particles have a lot of energy. And if you concentrate a lot of energy into a small volume to get very detailed measurements, a black hole will form. So this is something that should not happen in a fundamental theory. And so we have to find something. And in fact, this, I think, many people think, this is analogous to the breakdown of classical physics. So for example, electrodynamics at atomic scales. And this, well, we all know, this was resolved by quantum mechanics. And so in analogy to that solution, there's also a proposed solution for the breakdown of the classical description of the spacetime, namely non-commutative geometry. Of course, well, it comes in many flavors. It was developed by many people. I didn't put too many here because you probably know them better than me. So there are spectral triples, non-commutative ones, which are usually in Euclidean signature. Our world is Lorentzian, but there are also Lorentzian spectral triples, so this has been generalized. There are certain non-commutative spacetimes, like Snyder spacetime, Kappa-Minkowski, and also curved generalizations. So we know our spacetime is not flat, our universe, so one would need to get to generalize these examples also to curved backgrounds. And there is also strict deformation quantization, which introduces deformed non-commutative products. And well, okay. Many people are working on this. A particular realization that I learned about from my collaborator, Albert Much. I see a question, please.
Unmute yourself.
Yes. I have a question about the second point. Breakdown of classical physics at atomic scale was resolved by quantum electrodynamics, which is a quantum field theory, not quantum mechanics.
Okay.
Okay, so you have in this parenthesis, you have in particular electrodynamics. The problem is that electrodynamics is a field theory.
Yes.
So quantum mechanics is not enough. Yes. And then you have, of course, non-commutative observables, which are described in terms of annihilators and creators. Okay. And but they are not non-commutative coordinates in the space. So what they are talking about, Lorentzian and Minkowski space and non-commutative coordinates is something of different sort.
Yes.
Because it's not related to quantum electrodynamics. It's related
to also quantum mechanics resolve the problem of stability of atoms and also the
a single atom.
Ultraviolet catastrophe.
Yes, but it's a single atom. And in fact, it was about the hydrogen atom. Because if you have higher valency, you need more complicated methods than quantum mechanics. Quantum mechanics is not enough.
I totally agree with that. Maybe I should have put relativistic quantum mechanics, so quantum field theory, if you want.
Yes, yes, I agree. Yeah,
I agree with that.
But the point is that relativistic quantum mechanics doesn't exist. If you want to accommodate relativistic theory, quantum mechanics is not enough. It's inherently quantum field theory.
Yes, I agree. You need field theory to describe creation and annihilation of particles. I totally agree. But I mean, I'm working with quantum field theory later on, so I just want to make the analogy to give a motivation for non-commutative geometry. That's all this point is about. But
what I wanted to stress is the difference between creators and annihilators and non-commutative coordinates in the space-time. So there are different stories.
It's Ludwik Dabrowski. Hi, I think electrodynamics, even as classical theory, is from the beginning already relativistic because it's Lorentz invariant. But you had in mind probably quantum effects, just quantum mechanics, quantum effects which break down classical physics. So electrodynamics is not so important. I mean,
so the classical problem or specific problem I had in mind is, as was said, the hydrogen atom. So if you would have a point particle, an electron, orbiting around a proton, it would radiate and the atom would be destroyed. This is the problem I had in mind. But this is just an analogy.
In that sense. In that sense that, it doesn't radiate, in the stationary state. Good sense.
Exactly. Yes. Okay. And, well, as I said, I was introduced to the subject of non-commutativity by my colleague Albert Much. I don't know if he's in the audience. I don't see the list of people, but so he told me that something that a lot of people have studied is this Doppler-Fredenhagen-Roberts quantum spacetime, where the coordinates are really now non-commuting coordinates. I've given you the commutator here. So x nu is I theta with some constant matrix. And well, if you think about where the theory should be valid, then the entries of this matrix should be of the order of the Planck length. And said, okay, well, this is a postulate, but my question is, can this be derived? is this maybe something that doesn't need to be postulated, but comes already from things that we know? How can one realize these operators concretely as operators on some Hilbert space maybe? Is this compatible with Lorentz covariance? So in particular, if you do a Lorentz transformation and the right-hand side is constant and not just the two-dimensional, this in general will break Lorentz covariance. And then, well, with my other collaborator, Kyriakos Papadopoulos, so he was interested also in topology questions. What is the topology of such a quantum spacetime? How does it differ from the topologies in classical differential geometry? So these are questions I would, well, we tried to answer. We don't have an answer to all of them yet, but at least to the first question, I think, well, from the approach that we are using, the answer is yes. It's nothing that needs to be postulated, but it actually can be derived from things that people already do.
I have a question. Yes, I have a question. Yes. About the size of this right-hand side constant matrix. Why this is of the order of Planck length?
It doesn't need to be, but
why not, for instance, square of the length? Because the left-hand side is quadratic in
yes.
Yeah.
You're right. It should be a Planck length squared. You're completely right.
Yeah.
Okay. Yes. Okay. Thank you.
And in fact, so the result that will come out at the end of this talk will have a Planck length squared. Okay. So let's start with the framework that I'm using, which is the algebraic approach to quantum fields in curved spacetimes. What do we have as ingredients? Well, so it's essentially a generalization of quantum field theory to a curved spacetime. So what we need as an ingredient is a classical background spacetime, manifold M, metric G, and what is usually done, and I think most people are looking at, are globally hyperbolic spacetimes. Because what we need is a well-defined Cauchy problem. And for a globally hyperbolic spacetime, Bernal and Sanchez have shown that it can actually be foliated in a smooth way. So M is isomorphic to a direct product of R, which is the time direction, and some Cauchy hypersurface sigma. On this classical background spacetime, one introduces an algebra, which are free quantum fields. So it's A of M and G. It's a free star algebra. It's generated by the unit operator, does nothing. And elements phi of F, where F are, for the purpose of this talk, smooth complex exported functions on the manifold. So this would be the algebra of scalar fields. If one has other fields, for example, fermions or gauge fields, then these Fs would be smooth sections of some RS tensor bundle. This algebra is factored by various relations. Sorry, yes, please.
I have a question about this global hyperbolicity.
Can you switch on the camera, please? Tomek.
Oh,
camera.
Okay.
Camera.
Why do we need this decomposition into this Cartesian product? For well-defined Cauchy problem, having only vibration wouldn't be enough?
Locally Cartesian. Yeah.
We don't. So for the abstract theory, we don't need this foliation, but it's very helpful for concrete computations.
So it's not necessary condition for well-definedness of the Cauchy problem.
It's not a necessary condition, no.
Okay.
But as Bernal and Sanchez have shown, every globally hyperbolic spacetime admits such a foliation. So it's no loss of generality to take it.
So global hyperbolicity, could you remind me? What do you mean by this?
It's a condition. Well, there are various equivalent formulations, but I think the one that is useful here is that the Cauchy problem has a unique solution. So given initial data on a space-like hypersurface and a field equation, which I put in the point down like Klein-Gordon field equation, the solutions everywhere in the space-time are determined by this initial data.
So then it is a necessary condition. If this is the definition, and you said that to have
sorry,
delta,
Thomas. Sorry,
yes,
Thomas.
yes,
It's
yes,
equivalent.
Yeah,
it's equivalent. Yes, yes,
It's
yes.
equivalent.
I
It's
mean
corollary from the fact that the Cauchy problem is well defined.
Okay, now I
Globally well
agree.
defined.
Yeah, I agree now. Okay.
It's the same.
It's
That's
just,
a theorem.
thank you. Thank you.
Just to add, Tomek,
Yes.
I mean, basically, the most important physical condition is that there are no closed causal curves.
And this
So
is
which
equivalent
is sort of
global
reasonable from the physical point of view.
But mathematically, it is equivalent to global hyperbolicity.
Yeah.
Okay, thank you.
Okay. Yeah, as I said, so this free algebra is factored by various relations. First of all is linearity. This is something that doesn't have any physical reasoning for the moment, but it seems to hold for all quantum theories. So we know it holds on Minkowski, so then we take it for all spacetimes. We factor it by the field equation. So that means we set phi of pf to 0, where p is some normally hyperbolic differential operator. For example, for a scalar field, it could be the Klein-Gordon operator.
But sorry, this P is fixed once and for all?
P is fixed once and for all, yes. P depends just on the theory. So if one studies scalar fields, Klein-Gordon fields, P is this Klein-Gordon operator, once and for all.
Okay.
If we have a real scalar field, we have to take the hermicity condition. So the star operation just complex conjugates the test function f. And the last one, which is the condition that actually tells us that this is a quantum field, is the commutator. So the commutator of phi of f and phi of f star is proportional to the identity operator with some numerical coefficient. And this numerical coefficient in front is the smeared commutator function. So delta of f and f prime. And this commutator function is the difference between retarded and advanced fundamental solutions of the differential operator that we started with. So for this one, it is necessary to have a well-defined Cauchy problem, because then retarded and advanced fundamental solutions are unique. That's essentially the point.
So I have a problem understanding this formula. So this delta is just a difference of specific function, and this parenthesis f and f prime is what?
It means, so it's, yeah, so delta is a function of two arguments, x and x prime. And then if this means smeared with f in one argument and f prime in the other. So
you mean something like in fact, this delta is a distribution, but okay, so it is not a function of a space variable, but instead of you feed it with some smooth functions, and these functions are plugged into this delta, yes?
Yes, yes, yes.
Okay, so a value of distribution of two variables. So
maybe
many
by distribution.
It's a bi-distribution, yes.
Bi-distribution. Okay, okay.
Okay, very good. So then this is the algebra of free quantum fields. It's the free algebra factored by all these relations. And well, this delta fulfills something which is called a causality condition. Namely, if the supports of f and f prime are space-like related, then delta vanishes. So physically, that means that measurements which are made of the field at some space-like separated regions do not influence each other, because the fields commute there.
But sorry, you have written space-like related, so probably space-like separated, yes?
Yeah, so what I mean is that, well, yes, probably that's the correct terminology. That I'm a physicist, so sometimes I get this terminology wrong, but that's probably the right thing.
Okay.
So what I mean is that no point of the support of f lies in the causal future or past of any of the points of the support of f prime.
Okay. Okay, thank you.
On this abstract algebra, one has to define a state. So that's state of the quantum fields. That's a linear map which is normalized and positive. And these two conditions are needed for the probability interpretation of the quantum theory. So obviously the first one says that the total probability is 1. And the second one says that the probabilities are positive. Standard conditions. And the objects of interest in the theory, so the ones which in fact completely define the theory, are the so-called endpoint functions. So these depend on n test functions, f1 to fn, and are just the expectation values of phi of f1 to phi of fn. One can show, say, for a reasonable state, or another condition that one needs to put on the state is that these things are continuous in the test function topology. So that means that these Wn, the endpoint functions, are tempered distributions. And one can show, again, under reasonable conditions on the state, that these are actually moments of a probability distribution. This gives you the probabilistic interpretation of the quantum theory. And another thing that can be checked
I have another question.
Mm-hmm.
It's always so that these are moments of some probability distribution, since I recall that this is a very difficult open problem, realize those functions as a moment.
Yes. So, of course, not all states will fulfill this, but the states that are usually considered in physics or physically motivated ones, they fulfill this. One has to prove this, of course, but for all reasonable states that are looked at in physics, this is fulfilled.
Mm-hmm. Okay.
For example, for the Minkowski vacuum state, one can show that this works.
Since I recall that for interacting theories, this is an open problem. This is somehow related to this Young-Mills
Yes.
Millennium Prize problem.
Exactly. But so this one is the algebra of free fields. These are free quantum fields, no interactions. I totally agree. For interactions, that's an open problem, but for free fields, this holds for all reasonable states.
Okay, so the new thing is that now our manifold could be general curve manifold, but still
Exactly.
the theory is free, and then therefore this is somehow manageable.
Exactly. Yes. I will come to interactions on later slides.
Okay. Thank you.
And then, another thing that one can check is that the commutator function actually can be obtained as a difference between two two-point functions, namely the one of f prime and the one with the argument switched. So this is another condition on the state. Yeah, the state is not totally arbitrary. And the positivity condition in particular tells us that the two-point function must be a distribution of positive type. The nice thing about this is that it's a quite abstract algebraic framework. So in fact, I never have chosen any representation of A. And as is well known, for a field theory, there are many unitarily inequivalent representations. So things that one can derive in this abstract algebraic approach are independent of this problem. And that's the nice thing, I think.
Sorry, may I have a question?
Mm-hmm.
Is there any specific representation which will be the best for this construction?
Yes, there is one. I don't know if I have it on the next slide. Yes, there it is. So the concrete representation that one uses is obtained from the GNS construction, so named after Gelfand, Naimark, and Siegel. And in fact, the original construction was for C-star algebras, but it can be generalized to just a star algebra, in that what I showed you before. So this one gives you a Hilbert space and the preferred representation of the algebra on this Hilbert space. There's an invariant domain and a cyclic vector in that domain, such that the abstract state is really given by the expectation value of the represented algebra element in that concrete cyclic vector state, which is also normalized. One thing that people have been studied really a lot and in a lot of detail is if omega is Gaussian or quasi-free. So I'll tell you what that is in a moment. And in this case, one obtains the well-known Fock representation.
Sorry, Markus, just a completely stupid question. Why do you need to choose a domain? Why don't you take the whole Hilbert space? I mean, it's still a sister algebra. Why do you need to go unbounded?
It's not a C-star algebra, it's just a star algebra.
Ah,
so these,
you're right. Okay.
these files are, so if you want, if you have a quasi-free state, then the C-star algebra would be the Weil algebra. And these files would be the generators of the Weil algebra. And they are unbounded. So then one gets this dense domain.
So that's what we discussed. You might have unbounded generators of a sister algebra, but the generators themselves are not in the sister algebra, and the quality you're writing was not in a sister algebra. But that's with a Weil algebra. So you cannot say, I mean, it's a bit tricky to say that Weil algebra. Weil algebra is not a sister algebra, or
yeah. So no. So what I'm showing you here is just a star algebra, because that's what people actually use in practice for interacting models.
Yeah.
For free models, there is a direct connection with the Weil algebra where everything is nice. But one can generalize everything that, well, most of the things that people do there to star algebras, and then one has these additional restrictions.
Thomas.
I have a question about, could you come back to the previous slide? I'm still thinking about this supports of these functions being space-like related. How do you define this space-like related in a curved space-time?
Yeah, so if I have, so for a globally hyperbolic space-time, for each point, one can look at the future and past light cones. So what I mean by space-like related is that...
Sorry, but space, this light cone is something which is in the tangent space. It's not in the space itself. Are you prolonging this somehow geodesically? No, I don't know how.
Okay, so with the light cone in the space-time, I mean that you look at all light-like curves in the space-time, so where the tangent vector is everywhere light-like. Or time-like or space-like, whatever you want. And then what I mean by this support condition is that for any point x in the support of f, and any point x prime in the support of f prime, they are connected by a curve where the tangent vector is everywhere space-like. Let's say. So that would be one way to state it.
Very quick question. This delta of f prime was related to the commutator. So the other way to put it is that those operators commute if the supports of these functions are space-like separated, yes?
Yes, exactly.
So this is a kind of locality in this context of quantum field theory.
Yes, but locality on a curved space-time, well, at least in the mathematical or algebraic approach, has a different meaning. So this is called causality condition. Locality, I think, come to it also later on.
Okay.
No, not really. Okay. You could say it's a locality condition, yes. But so the name that people use is causality.
Okay, thank you.
Okay. That's it, yes. Another condition that now needs to be put on the state is the so-called positive energy condition, which translates into a condition on the wavefront set of the endpoint functions, which is also known as a Hadamard condition. And I've given you here the condition explicitly for the two-point function. So the wavefront set of the two-point function needs to be contained, well, in this expression. Yeah, so this is elements from xk, x in the manifold, k in the tangent space. So k needs to be non-zero future directed, k prime non-zero past directed, and then the points, well, xk and x prime minus k prime need to be related by this symbol tilde, and that means that there is a null geodesic between x and x prime, and k and minus k prime are tangent and parallel transported into each other. So it's a technical condition, but it can be checked more or less easily for concrete examples. So, well, as a very concrete example, I've given you the two-point function in Minkowski spacetime. So it depends on the 2 points x and x prime. More questions? No. Okay. This 2-point function is a distributional boundary value. So, well, you see it's essentially the Minkowski distance, or 1 over the Minkowski distance, but the boundary value as you approach it from inside the light cone, I think. And then one can check, it's a short calculation, that this wavefront Z condition is fulfilled. Physically, that means that the state has positive energy, so there's nothing strange going on. And then for the higher endpoint functions, this wavefront Z condition just means that the cumulants for n greater 2 are smooth functions, so their wavefront Z is empty. And just to recall your definition of a cumulant, I've given the example for a 3-point function. So the 3-point cumulant is just a 3-point function, and you subtract the symmetrized version of a 2-point function, hence a 1-point function, and add back some 1-point functions. So this thing must be smooth. Not the distribution, but really a function. Okay. And now I said before that if you have a Gaussian state, then this construction gives you, or the GNS construction gives you a Fock space. And now I can tell you what a Gaussian state is. Namely, it's one where all the cumulants with n greater 2 are 0. So it's a very simple state. Everything is determined in terms of the 1 and the 2-point functions. And well, one can prove very nice results on these states. So, for example, for 2 Gaussian states, one gets unitarily equivalent GNS representations. So one is in a very nice situation if both of these states fulfill the Hadamard condition and the Cauchy surfaces are compact. And this is now where, for example, this foliation enters as well. But it's just the flavor of results that one can prove. I've given you some more examples. Well, we're at some temperature. It's not too cold here. I hope also in Warsaw it's not too cold. So if one looks at the thermal state at some temperature greater than 0, then the 2-point function is a bit more complicated. So, well, I've given it here to you as a Fourier integral, and one can show that also in this case the wavefront Z condition is fulfilled. And, well, not the most. Yeah, please.
From this condition of being unitary equivalent, could you somehow say how many unitary inequivalent representations are?
This I don't know, but the point is that for physical reasons, the state needs to have positive energy. Anything with negative energy is not physical. And this condition means this Hadamard condition. And you see, if both states are Hadamard, then they are always unitarily equivalent. So I would say that anything else is not physical in that case.
And could you please go back to this definition of being Hadamard? It was related to this.
This is this wavefront Z condition.
Yes. Physical.
So essentially, what it means is that, say, for any points which are not connected by a null geodesic, it's a function. And if the points are connected by a null geodesic, then it's only singular if the covectors are tangent to this geodesic and are parallel transported one into each other along this geodesic. So it's a very specific condition on when this 2-point function can be singular.
But I'm a little bit confused about this condition. You have written that this wavefront of W2 is contained in some set, and where this wavefront is defined.
Okay. I didn't know that. I thought that people knew what a wavefront set is. Okay. So you know what a singular support of a distribution is?
Singular support? I know what a support of a distribution means.
Okay, so well, okay, let's go to the example here that I've written down for the Minkowski metric, this W2. So you see that let's forget about the epsilon for the moment. So then you see that if the difference between x0 and x prime 0 is the same as the difference between x and x prime, the vector points. So when you're on the light cone, then this is singular. Yeah, it's 1 over this, say, Minkowski distance. So this is divergent on the light bond.
Okay.
So, and anywhere else it's finite. Yeah, so if the 2 points are not light-like related, but space-like or time-like, then this is just a function. It's a well-defined function. So the singular support of a distribution is exactly where it's not a function.
Okay.
So that, you know, if you smear with some localized test functions, then you can do it in the function sense if you're not on the singular support.
Okay.
And the wavefront set, in addition, tells you if you now go to these to the singular support, so these points where it's a proper distribution, go to Fourier space, then you know, so being singular in position space means there is slow decay in Fourier space. So the wavefront set is the set of all the directions in Fourier space where it doesn't decay exponentially fast.
Okay.
So it tells you in addition the directions in which the distribution is singular. And there's a way to generalize this to curved space-time. So essentially you localize at some points and then you can go to a sort of local Fourier space.
Okay, thank you.
Of course. Okay. Yeah, so our space-time is not flat. We know that. So a good description of the geometry is actually the Sitter space. And I've also given you here the 2-point function for the Sitter space, which is a hypergeometric function with a quite complicated dependence on coordinates. Maybe we don't need to go into details here.
Sorry, Markus, please allow me. I have another stupid question. I'm
course.
looking at this limit with epsilon going to 0 from the right. And when I look at the formula, I don't see what goes wrong if I put epsilon equal to 0. I'm looking at the formula. I take epsilon equal to 0. Why does it go wrong?
So this limit needs to be taken in the sense of distribution. So after smearing.
In the sense of distributions. Okay.
Yes.
Okay. Thank you.
Of course. Okay. And now we come to, well, this was the free algebra. So I've given you a state. I've given you the algebra. And now one wants to do interactions. And for this, one needs to do additional work. So first of all, one needs to look at tensor products of test functions. And in this case, it's, well, we know that, say, the space of smooth complex supported functions, the nth tensor power, is contained in the space of smooth complex supported functions on the nth tensor power of the manifold. So this is a sort of trivial enlargement of the algebra. So that's it's just a dense embedding. And then for physical reasons, one would also like to take distributional limits. So we know that the space of test functions is embedded in a distribution space. So for example, what one would like to do is to take some F2, depending on 2 arguments xx prime, and take a limit where this becomes proportional to a Dirac delta. This is problematic because if we go back to the example of the 2-point function that I gave you and the point here below, if we set the points equal, this is exactly where this distribution becomes singular. So we cannot take that limit, but we need it for physical reasons. And the solution of this is, well, one just subtracts the singular terms and defines so-called normal ordered products. So this is now, it's a linear combination of products from the algebra that we already have. But, so we partition, let's say we take n elements, f1 to fn. We take from this all disjoint ordered pairs I and j. We take the product of all k which are not in this sum of pairs. And for all pairs, subtract the term h2. And h2 is the universal singular part of w2. I don't want to define it here in detail because it gets a bit technical, but it's the one that it's common to all Hadamard states, thanks to this Hadamard condition. And well, you can see it's just a linear combination of what we have. So these are still all elements of the algebra, these normal ordered products. There's another question?
No, I don't see any. No.
Okay, sorry. And the fact is now one can show that for these normal ordered products, one can take distributional limits, such as the one that I've written above, if the wavefront set of that limit is not contained in well, the set v plus n cross v minus n. So yeah, if it's not all, if not, that's not all future pointing or all past pointing.
You have said not contained, but the condition which is written on the slide is being disjoint.
Yeah, sorry, that's what I meant. Yes, you're right. Yes.
Being disjoint, okay.
Yes. So you can view this as the closure of this algebra in a suitable topology that takes into account this wavefront set condition. And the nice thing, well, what one can prove, or which has been proven by people in the field, in particular, what I've written down there, Sanders, Hollands, and Ruan, is that the algebra that we start with, or the trivial enlargement to n's powers, is dense in this closed algebra. The star operation and the product that we had are continuous, and any Hadamard state that we had before extends also to a continuous state on this closed algebra. And the other way around, any continuous state on this closed algebra restricts to a Hadamard state on the one that we had before. So, okay, very nice. We have now a slightly larger algebra where we can take certain distributional limits. And just to give an example, so for people who like to do concrete computations, as I said, we want to take this limit where this function f2, can you see the cursor? Yes. Becomes a delta times some other test function of this phi tensor phi. So a double product, normal ordered. Normal ordered just means subtract the singular part. So we take phi tensor phi, subtract the singular part. And then the limit exists. It gives what is called the Wick power, second Wick power of phi. And this has a finite expectation value, for example, because h2 subtracts the singular terms of the 2-point function, and then I can take the limit. And then it's just the difference is an ordinary function, and there I can take the limit of coinciding points. And so, okay, now comes the thing what is called locality in this framework. That's why I used causality for the delta before. This construction gives you covariant fields. So that means take two different spacetimes, M and M prime, and an isometric embedding that also preserves the causal structure. So that means that pull back of that embedding acting on the metric G prime of the second spacetime gives you back the first one. Then these fields transform as they should. So that means the normal ordered product of fields on the new spacetime pulled back to the first one is exactly the same as if you would first pull back the field, then take the normal ordered power and evaluate in the first spacetime. So this is a condition that is very restrictive, that tells you your theory plays well with well, differential geometry, with properties that you would expect. You don't do anything strange. Mm-hmm.
I'm a little bit confused by this notation, this M prime, G prime in this normal, this covariant fields only indicates on which manifold it acts, or?
Yes, so G prime is the metric of M prime.
Yes, that's clear. That's clear, but I mean a line above in this expression. Yes, here.
Yes.
So this only, in this place, it only indicates on which manifolds.
Yes, so we take the normal order product of phi k on the second spacetime, and then pull it back to the first one, to the algebra of the first spacetime.
So this is not necessary, but only for pedagogical reasons, yes?
Yeah, so if you have two spacetimes, you do the same construction with the algebra and everything on each spacetime. And then you need to relate fields on one to fields on the other, which you do via this pullback.
Yes, but you said evaluated on something, and I was confused by this.
Okay, sorry.
By this phrase. Okay.
So this means, well, okay. So if you do the construction on the second spacetime,
okay, I see.
Pull back all the options, all the objects that appear to the first one, you get the same as if you just take the field, first pull back, and then do the construction. So these things commute in a sense.
Okay, thank you.
Markus, sorry to interrupt you, but I cannot resist telling you this. I wanted to recall what normal product means, because you keep on saying normal product. And it's very dangerous because there is a company called Normal and they sell some products. So first what you pops out are products of a company called Normal. And only then it's like normal ordering, but first what is spitted out by Google is normal product, company Normal and its product. So, but now I looked it up. I know what it means, normal ordering. Okay.
I think that company came afterwards, but so that's the terminology from quantum field theory. Yeah, so we have, you said there was this guy working on quantum gravity, maybe he knows it. Essentially, it comes from the fact that if you do a quantum field theory on Minkowski spacetime, you should normal order your creation and annihilation operators to get finite. So this is if you want the analog of the construction on a curved spacetime. If you do this on Minkowski, you get exactly the same as if you would just normal order creation and annihilation operators.
Okay, great, thank you.
And the last thing that one needs are so-called time-ordered products. So these are just maps from classical local and covariant polynomials in the field on your manifold into this completed algebra A-bar. They are symmetric in their arguments, and they can be constructed inductively. So if you start with just one, say, classical polynomial, phi to the k, for example, it gives you the normal ordered one. So this which is defined as I've explained to you on the top of the slide or the previous one. And then if you have more than one entry, they fulfill what is called causal factorization. So you take the support of these fields smeared with some test functions, a1 to an, and whenever this support of the first n things does not intersect the causal path of the support of the fields B1 to Bm, then this product factorizes. So it's just really a product in the algebra. And one can show that this condition determines the time-ordered products up for all say space-time arguments or for all supports, except to the case where everything is supported on the same point, on the same region. And to define these time-ordered products as, say, proper distributions, one has to extend them to the diagonal. This is what in flat space corresponds to renormalization. One can show that one can always do this. It's a bit, it's long to make this precise, but it was done by Holland and Wald about 20 years ago. I don't want to go into details at this point, just to say that one needs to do this. Okay, and now we come to interactions. And this is last slide on this algebraic approach. We all know, well, maybe we don't, but there's a millennium problem on doing things non-perturbatively, so really, fully. So the only thing we can actually do are do a formal perturbation series or formal power series. So that means that we take our free quantum field and we add some interaction term. For example, a very simple model would be a phi to the 4 interaction term, which I've given you here. It depends on some coupling lambda, which is, again, the test function, let's say. And then one looks at formal power series in this coupling with values in the completed algebra in A bar. As I've written you here, so this is an A bar of lambda. Maybe if you are, there's some parameter H bar that you can also put if you want. And now your interacting fields are defined via this formula. So it's called Bogoliubov formula. You take two time ordered products. the second one incorporates the field, the free field that you want to look at, phi of f, and tensor powers of the interaction, whatever your theory is, whatever your interaction is, and you multiply this by another time-ordered product, exponential of the interaction, but take the inverse in the sense of formal power series. Why this definition? Don't ask me, it works. So one thing one can show is that it satisfies the interacting field equation. For example, if you have the Klein-Gordon field, then on one of the first slides, I said that the free algebra needs to be factored by phi of PF with the free phi. And now for the interacting phi, one can show that one doesn't get 0 on the right-hand side, but the, say, part from the interaction that one would like. So for example, if one has phi to the 4 interaction, then one gets 4 phi to the 3 on the right-hand side. And this power is then again defined by the volume formula.
Sorry, Markus, I have two more stupid questions. So one, why is it a formal power series in lambda? I understand in H bar, but why in lambda?
So yeah, actually it's not easy to see that it's a formal power series in H bar, because as you can see from the formula, what enters is 1 over H bar. So the second one actually...
That's true. That's true, but that's okay. At least I see H bar and I see exponential. Yeah. Okay, I see H bar taking to arbitrary power, though negative. This is true. But lambda, I'm completely lost. Why is the power series in lambda?
Because so the exponentials are to be understood in the sense of formal series. And as you can see...
Sorry, you have this S interacting and here's lambda, of course. Yes.
Exactly,
I'm so sorry. Okay.
Exactly. Okay. No worries.
Okay. And now I'm looking at this bar. So if you would delete this bar, what would it mean?
Well, you need the bar because, so as you can see, so this phi to the 4, this is defined in the same way as, say, the phi squared on the previous slide. So via this normal ordering procedure with the limit.
Yeah. I don't question that you need it or don't. I'm just trying. I want you to tell me what it means to take this bar. It's some kind of closure or what? What?
Yes. It's
just a closure, right?
It's a closure,
okay.
Yes, in a certain topology. Yes.
Mm-hmm. Okay. Tomek.
I have a question about this lambda. So now lambda could be a function on M.
Yes.
So what do you mean by this formal power series with variable lambda, formal variable lambda? How a function on M could be a formal variable?
Well, if you want, you could split it in two parts, say lambda times f, and then lambda is really a formal variable and f is a function. So I'm being imprecise here, you're right.
Okay.
And then the algebra of interacting fields, so the interacting field algebra, that's now a sub-algebra of this formal power series, which is the one that is generated by the interacting fields phi, defined by this formula there, and their powers. And the interacting endpoint functions are the expectation values in the same state that was used in the free algebra of these interacting fields. So they're also formal power series in lambda and H bar. And so this is the framework that I'm using, which it's a lot of things to stomach. I understand that. I mean, it was functional analysis, differential geometry, some algebra, but it's a mathematically precise version of what physicists have been doing, well, since the 80s, let's say. Okay, it is what it is. One can compute things with it. So then let's come to the second part, perturbative quantum gravity and relational observables. Now we want to apply this general theory to a very concrete model, namely perturbative quantum gravity. So all, say, physical models come from an action. So what we take is we take the Einstein-Hilbert action for gravity, which, well, I've written you down here, contains the Ricci scalar of a metric G and the cosmological constant lambda. And I've also introduced this parameter kappa, which is just a rescaling of the Newton's constant. As we all know, this is invariant under diffeomorphisms, well, let's say compactly supported, with some parameter lambda. And the only thing that we need is the first order. So that means where all geometric quantities transform with a Lie derivative, essentially. Since we do perturbation theory, we have to take a background, let's say background metric G, and we expand our full metric G tilde around this background. So we take G plus kappa times H. Kappa is therefore, let's say, kappa is the analog of lambda in the previous slide. So it's a formal parameter, and we look at formal power series in this parameter. And then let's say we look at diffeomorphisms with a small parameter. So let's take psi of order kappa. Then the diffeomorphism symmetry of the full series, of the full metric, translates into a gauge symmetry for this for the metric perturbation H, which you probably all know. It's just a symmetrized derivative of the parameter plus some higher order terms. How does this fit in the framework that we have before? Well, we need to first get the free theory and then the interactions. And it's not difficult to see that if you plug this expansion in the Einstein-Hilbert action and assume that the background metric solves the Einstein equations, so r mu nu minus 1/2 r g mu nu plus lambda g equals 0, then this Einstein-Hilbert action splits into a term which is quadratic in the perturbation H with some differential operator P and some higher order terms which are at least of order kappa. So the part that is quadratic, which I've given you here explicitly, that's the action of the free theory. So this P is the analog of the Klein-Gordon operator. It's a differential operator, a bit complicated. And all the remainder is the interaction. There is a bit of a problem because this gauge symmetry for the metric perturbation translates into the fact that the P... sorry, there's a question. Yes, please.
Yes, I have a question about this gauge symmetry. So the first summand of this, what you call gauge symmetry, is simply the action of the diffeomorphism.
Everything is the action of the diffeomorphism.
So I don't understand then this O of K, because the first two summands is the Lie derivative of this psi, psi with respect to this acting on this perturbation H.
Yes. Okay. So what you would get is that delta psi of the full metric G tilde is the Lie derivative of the full metric G tilde.
So we are starting from killing vector fields for the full metric G tilde.
Doesn't need to be killing. It doesn't need to be killing.
Not killing.
Not killing. No, it doesn't need to be killing. Arbitrary vector field for the full metric, but since I'm doing perturbation theory, I say it's of order kappa, so it's a small vector field, if you want. And then if you expand the Lie derivative of the full metric in orders of kappa, you see that the background doesn't change, but H changes with the Lie derivative of the background metric, and then there's the Lie derivative of H itself, which are these order kappa terms. So it's really just take the Lie derivative of the full metric of G tilde, plug in a psi of order kappa, and compare different orders in kappa.
So by O, capital O of K, you mean something which is of order of K, but with coefficients
of order
functions on M.
Yes, exactly.
Bounded functions on M. No, not even bounded functions.
Well, something compactly supported, probably. Smooth, compactly supported.
So you're so your symmetries are compactly supported. Okay.
Yes, because otherwise you have to deal with things at infinity, and that's becomes quickly complicated.
Yes.
So let's say compactly supported. Yes.
Okay, I agree. Thank you.
Of course. So yeah, this gauge symmetry immediately translates into the fact that the operator P annihilates such symmetrized derivatives. Okay, I put arbitrary f, let's say compactly supported again. And that means, of course, that there are no unique, advanced, and retarded fundamental solutions. Yeah, so already the first step in the construction at this point seems to fail. Of course, there's a way around, otherwise I wouldn't be working with this. But this is one of the issues. And the second issue is that P is not normally hyperbolic because it contains second derivatives in a form that is different from just nabla squared with some metrics. So this makes also the construction of these fundamental solutions, even if they would exist, quite difficult. Yes.
I'm still thinking about this name, gauge symmetry. If H was, let's say, a potential of some gauge theory,
yes,
then the gauge symmetry is well defined because it comes from automorphisms of the principal bundle. But what's the meaning of this gauge here in this context of this deformation? Why is gauge symmetry?
Because you can use the same methods as you would do for electromagnetism, for say, this U1 gauge symmetry, to treat the problem. So it's completely analogous, except that now it comes from diffeomorphisms.
But general relativity is not a gauge theory. Or do you have some models similar to gauge theory?
No, GR in general not, but if you do it perturbatively, yes.
So perturbatively,
exactly.
General relativity looks like
a gauge theory.
Theory.
Yes.
Okay.
Yes.
Okay.
So what's the gauge group? What's the gauge group?
I don't know what it would be exactly. Sorry.
Okay.
I mean, if this were a vector potential, then the gauge symmetry would just be the gradient of some arbitrary function. And now it's not a function, but a vector value, a vector. So I'm not sure if there's an exact group, but there's an algebra certainly. And I mean,
sorry, I have a problem with this gauge. I don't understand. So the point of gauge is that objects you are playing with, they are not tensors, in fact, with respect to some representations of some gauge transformations. But here, everything is a tensor, which is
it's a tensor. Yes.
So I cannot see this gauge action here.
It's yes. So the full metric is a tensor with respect to diffeomorphisms that transform everything. When you do this perturbative expansion, in a sense, you break that because you're decomposing a tensor into two parts: the background metric and some perturbation.
But both parts are tensors. Under diffeomorphisms, they behave like tensors. Are you using some preferred coordinate system? Which
no, I'm not. But I'm only looking at small.
If not, they are tensors. So
I'm only looking.
What could be this gauge action? I cannot see the gauge action.
I'm looking at small diffeomorphisms of order kappa that leave the background invariant.
Yeah.
So there, what I'm doing is so H is a tensor with respect to background diffeomorphisms, but not with respect to these small diffeomorphisms.
I don't understand this. Diffeomorphisms act on everything. All this G mu nu tilde, G mu nu, and H mu nu, they are three tensors. If you change the coordinate system, they transform in a usual way.
No, because think of a coordinate transformation. Take a coordinate transformation, which is formal series in kappa, formal power series in kappa.
Yeah.
Then you will see that under the part of order kappa to the zero, so independent of kappa, the background metric G is a tensor, H is a tensor. But if you look at the transformation law at H, it takes contributions from first order and kappa of that coordinate transformation, and it does not transform as a tensor anymore. It's the same as if you would take, say, usual gauge symmetry, decompose your gauge field, your vector potential A, into a background field and some fluctuations, and only look at transformations that leave the background really invariant.
Wait a moment. So they are not arbitrary diffeomorphisms?
Small ones of order kappa. So you forget in a sense about the background. The background is fixed in this perturbative expansion.
But introducing a parameter kappa doesn't change. Then you have simply a family of diffeomorphisms depending on the parameter kappa.
Yes.
But they are honest diffeomorphisms.
If you look at all orders, yes, but not if you look at one specific order.
Okay, but in specific orders of the expansion with respect to kappa, you obtain some functions which are independent of the choice of coordinates. So what is this? So what is the source of any idea of gauge here?
Well, maybe the name gauge symmetry is a misnomer, could be. But there is this transformation which, for practical purposes, if you do the computation, for the problems that appear if you want to quantize a theory, behaves exactly like, say, the U1 gauge symmetry.
Okay, but until you break diffeomorphism invariance, until you are introducing some preferred coordinates, you cannot see the effects of non-being tensorial here. Everything is a tensorial.
I mean, I have a preferred background metric. I have a fixed background.
No. I'm not talking about preferred metric, because it's affected by diffeomorphism as any other thing here. I'm talking about a preferred coordinate system. If you do not have a preferred coordinate system, not the background metric, you cannot see any effect of some gauge, because everything transforms with respect to some one parameter family, where kappa is a parameter of family of diffeomorphisms, and everything is consistent. So the effects of gauge, it's a compensation of some non-consistency if you are, for instance, trivializing principal bundle. So for the principal bundle associated with this orthogonal or Minkowski kind of orthogonal frames, it would be like a choice of an orthonormal frame here. It's not about diffeomorphism. It's about taking this orthonormal frame, and then differentiating something. You can produce some non-tensorial things which have to be compensated in some kind of gauge to make them like invariant after this compensation. Yeah. So.
No. Okay. Now I think I understand what you want to say. But so what I mean when I say that the background metric is fixed, I also mean that the coordinate system on the background metric is fixed. Yes.
Yeah. I don't have a problem with that. I have a problem with using the name gauge symmetry, because I cannot see any kind of gauge symmetry here.
Okay. Then don't call it gauge symmetry. I mean, there's this transformation. Let's not call it gauge symmetry. There's this transformation, and that makes problems for the quantization of the theory.
Okay, so now since we removed gauge in the sentence below, I'm missing a subject. Who obtains action? You mean we? You see, I read the sentence in English. If blah, 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 obtain action. There is a subject missing, right?
Yeah, okay, yes. Let's call it obtain transformation, symmetry transformation.
Okay.
So as I said, the main problem is that in this free part of the action, the differential operator P does not have unique advanced and retarded fundamental solutions. So the first step in the quantization program, which is to construct a free field algebra, fails. That is the main point that I wanted to make here. Okay, forget about the name gauge. What one has to do is forget about gauge everywhere. But this is the terminology that people use. This is why I put it. So what one has to do is one has to add a term to the action, which depends on some parameters. So in this case, the parameter alpha and the parameter beta, and which is such that the sum of the action previously and this extra term gives an operator P alpha beta that has nice properties. So, for example, if one takes alpha equal to beta equal to 1, what people name in honor of Feynman, the operator P11 is a normally hyperbolic operator. One has to do an operation called trace reversal, but that's just something very easy. And this P11 has unique advanced and retarded fundamental solutions. So that means that the program that I told you in the beginning, this algebraic quantization program, can be followed exactly step after step to obtain the quantum theory with kappa as the say formal coupling parameter. Of course, the question is, are the results, and in particular the correlation? Sorry, yes, please.
Sorry, I have another question.
No problem.
By this fundamental solution, people usually mean in theory of differential equations that you have some distributional solution, and all solutions can be obtained by the convolution of this distribution. Yeah, but the problem is that if you are talking about this convolution, you are using the structure of an abelian group, topological abelian group on Rn. Which you don't have now.
So in Minkowski spacetime, the fundamental solutions depend on the difference of the arguments, x minus x prime.
What does it mean? In some preferred coordinate system?
Now we have fixed the background, so there's a coordinate system on that. But
so you have a preferred coordinate system. So your background is flat, for instance, and you have this flat coordinate.
It could be, a background could be de Sitter, it could be some cosmological spacetime, it could be a black hole spacetime with the corresponding coordinates.
Yeah, but what is the fundamental solution on the de Sitter space? On the flat space, I can imagine.
It is the function in the last point where you replace the minus I epsilon x0 minus x0 prime with a minus I epsilon and take this distributional limit. That gives you the fundamental solution.
Yeah, but how do you convolve this distribution to obtain every solution?
This is what I wanted to say in the beginning. So in Minkowski spacetime, the corresponding one would be the one here in the third line, and you see in Minkowski. Wait. And in Minkowski, it only depends on the difference x minus x prime. Yes. So if you convolve, you take this function, multiply by a function f of x prime and integrate over x prime. But you can do the same if it depends on the 2 points separately. So now this depends on x and x prime separately, at least in this factor. You don't see it here, but in general it will be. And you just multiply this by a function of x prime and integrate with the volume element of your background metric.
So now you are so now your definition of the fundamental solution is an integral kernel of some operator instead of convolution with some function, with some distribution.
No, but these things are it's the same thing expressed in two different
ways. No, it's not the same thing, because in the de Sitter space, the difference of coordinates doesn't make sense, which is needed in convolution.
What I'm saying is that the Minkowski case is a special case of the theory in a general curved background spacetime, globally hyperbolic, where the kernels of these convolution operators depend on the points separately and not just on the difference. That's what I want. That's what I'm saying.
So, I mean, so now
this is standard, I think.
Oh no, it's not standard. Now you are calling composition of integral kernels. Now you are calling convolution, which is highly misleading because it's a completely different thing.
I'm not composing integral kernels. This is a distributional kernel. In Minkowski, this is a distributional kernel. I mean,
in convolution, you need a difference of coordinates. How do you subtract coordinates into the de Sitter space, which is a non-linear thing?
Okay, then let's not call it convolution. Everything I've read calls it convolution.
This was my point. Yeah, do not confuse things. Yes. Please.
Okay. Then I will not do
that.
No
gauge, no convolution.
No gauge, no convolution. Okay, I'll take that into account.
Yes.
Then let's also just skip what I've written here on the slide. I think months ago you had a nice talk by what's her name? The Italian from Göttingen, Roberta Iseppi, on the BV formalism. So this BV formalism is the one that people use to treat such theories with some symmetries, and this can also be done in this case. So it's a bit more, let's say, it's a bit more complicated than what I had on the first slides, but it can all be done properly, let's say. And the main point that comes out of the theory, let's say for our purposes here, is that the results of the theory, so the correlation functions of some physical observable, does not depend on these parameters alpha and beta that one introduces by adding this extra term, if the classical field is invariant under the transformation that we had before. So in this case, in this sense, the quantum theory does not differ too much from the classical theory, at least in this formal perturbation theory. So if one can find classically something that is invariant under this transformation, then also in the quantum theory, after this quantization, the correlation functions will be invariant. That is the main point. And okay, so how does one do this? Now let's go back to a real gauge theory. For example, Yang-Mills theory, where one has a Lie algebra G and a group of that. In this case, it's very easy to define classically invariant observables, namely traces or products of these. So one of the examples, or let's say maybe the most well-known example, is this trace of F wedge star F, for F the field strength of the connection. So I believe this is more, this I can call gauge symmetry, yes? Or gauge theory. Okay,
this you can.
Very good.
Yes, I agree.
Okay, very good. So now, if you go by analogy, yeah, so I'm not calling it gauge theory, but by analogy, the analog of a trace would be integration over the manifold. But that would mean that there are no local observables, because, well, that's a very naive way to put it, is that diffeomorphisms move points, so nothing local can be invariant. And this can even be shown, let's say, a bit more formally. Let's take some tensor field. Forget about local covariance. Let's take a tensor field, which has a series, formal power series expressed in kappa, and use the Stewart-Walker lemma. And the Stewart-Walker lemma tells you that if at order n+1 in this expansion, it is invariant under the symmetry, then at the order before, at order n, the corresponding coefficient of this tensor field must be a linear combination of deltas, Kronecker deltas, with constant coefficients. And of course, these are very boring because, well, let's say observables in physics, they're not just constants. I think things should be fields, they should depend on space-time and so on. And that would mean that there is no local observable in gravity, which, at least from a physical point of view, doesn't make much sense, because we certainly see gravity locally. If we throw a stone, it falls down. And the solution of this, well, it's probably known since, well, it's known since a long time, so people have been studying this in classical GR, at least since the 60s, are so-called relational observables. And this one well, how are they defined? It's the state of one field, one dynamical field, not a background, of the theory with respect to another one. And then very, let's say, easy to see is that, maybe not easy to see, but it looks very good, is that each transforms under diffeomorphisms, each of these two fields. Yes, please.
Sorry, again, I have a question
No problem.
about these tensors. You have these tensors, okay?
Yes.
And you have this condition that some expansion coefficient,
yes,
of this tensor is a linear combination of deltas with constant coefficients. How it could be? Because deltas are deltas. But deltas of what? There's something missing here.
Okay, yeah, that might be again the physicist notation. So I mean, Kronecker deltas delta mu nu, if you have a 1-1 tensor field. So let's if you write it in index notation, let's say take a T mu nu.
Okay, so then I don't understand what is delta here, because if I take taking a linear combination with constant coefficients of these deltas, whatever they are, then you obtain a tensor. So deltas are tensors. What is this delta?
Yeah, how can I write something on the slide? I know I have it. Hope. Draw. Yes. So what I mean is, for example, it's just let's say a constant times the delta.
So these deltas must be of tensorial coefficients.
Yes. This is what I mean with delta.
I don't understand at all. What are these deltas?
Okay. How do you? Okay.
It's not a measure. It's a measure taking.
No, it's not a Dirac delta or anything. It's just.
I suppose so. Yes. So this must be some kind of Dirac delta with coefficients in tensor fields.
No. So for example, say take the Ricci tensor.
Yeah.
So Ricci tensor I would write as R mu nu.
Yes.
Because it's 1-1 tensor. Yeah. So this is just C delta mu nu. So in a sense, this is the identity, constant. So the Ricci tensor is a constant times identity. If I would write this with lower indices, that would mean that it's
Kronecker delta.
Yeah, I said Kronecker delta. Yes.
Kronecker delta. Okay.
Yeah, he said it. He said it. Yes.
He said it. This is Kronecker delta.
Sorry, that. I hope the connection is good.
But wait a moment. There are plenty of tensor fields.
Yes.
Which are not proportional, or even combinations of delta Kronecker deltas.
Yes. So that tells you that T at order n+1 is not invariant under this transformation. You just take the converse of this lemma. Of course, there are plenty of tensors that one would want, that one needs, which are not like this. So that means these things are not good observables.
So what is this assumption about this tensor field, in fact?
Which one?
T.
No, yes, which assumption?
Where
the vanishing limit, right?
Sorry?
The vanishing limit, right, Tomek?
No, it's not a limit. What is this?
Oh, sorry, not the limit. No, sorry, just
delta psi. Is it a Lie derivative of this tensor field? What is?
Yes.
So I expect that this n+1 in parentheses, it means a coefficient in the formal
expansion.
series.
Yes. Exactly.
Okay. So I understand this, and then you are taking the Lie derivative of this tensor with respect to this vector field psi.
Yes.
Okay. Good. So I understand this. And then the claim of this Stewart-Walker lemma says that it is not only of very special tensorial type, For instance,
Yeah.
it is one covariant, one contravariant.
Yeah, or if you have more things, more, yes.
Yeah. So from the beginning, T is not an arbitrary tensor field independently on this condition that delta psi of T blah, blah, blah is equal to 0. But the type of the tensor to make even this problem well formulated is very restricted.
Yes, of course. Yes, yes. So for all tensors that are not of this type, then it can never be invariant under this transform.
So from the beginning, this T must be one index covariant, one index contravariant. Yes.
Or 2, 2, or 3, 3, or 4, 4. So you can have many Kronecker deltas.
So why do you write covariant tensor field? Because you wrote covariant tensor field.
Yeah, because, okay, so sometimes in physics, people consider strange things. So I just mean a tensor field in the usual differential geometry sense.
Okay.
So no covariant, no convolution, no base.
No, nothing of the sort.
So definitely the number of contravariant indices is the same as the number of covariant ones.
Yes.
Yeah.
But of course, with the metric, you can always, raise and lower things.
Okay. Thank you.
Of course. Okay. How do I remove these things again?
Yeah, I cannot help you here.
Yeah, no worries. I think I can find it out. Yes, okay, very good. So people have, what people are considering are fields observables invariant under this transformation, and the only thing that can happen is that they are relational. That's the upshot of this. So one needs at least two fields and sort of define their relative state. I will explain to you how to do this on the next slides. Okay, so let us assume that we have four scalar fields. Four scalar fields. This is why I put the index in parentheses. It's not a tensor field, it's really a scalar field. They can depend functionally on your metric perturbation or on something else if you have a more complicated theory. And I want them to be scalars, so I've written you down the transformation of a scalar. That's, of course, well known, I think. Since we're doing perturbation theory, we choose a certain background that we want to look at, and we impose, or we choose our four scalar fields such that the map on the background, so from the background coordinates small x mu, which are also fixed now, to the value of these four scalar fields, where you set everything else to 0, that these maps are injective. And then we define the maps alpha, which is the inverse of the first one, composed with this x0. If one does formal perturbation theory, as we do here, then this alpha is well defined, and it's well defined in general if h would be, say, sufficiently small, because for h equals 0, it would just be identity. Now, as I said, in what we do in perturbation theories, we look at small diffeomorphisms, so ones that leave the background invariant. And then under these diffeomorphisms, it's quite easy to see that alpha transforms in the way that I've written. So just with the inverse of whatever your map psi is. And now, it's clear, I think, how to construct an invariant observable from any tensor field, namely just by composing with this map alpha. I mean, it's a one line to see that it doesn't transform under a small diffeomorphism, so one that leaves the background invariant. And so this is the definition of a relational observable. Given such a map alpha, which is constructed from these scalar fields, any tensor field can be made into something that doesn't transform by this construction. So it's relational with respect to these scalar fields X. Yes?
Another question. What is this composition of a tensor field with a diffeomorphism?
Where?
I see
Which?
this
penultimate line, no?
Calligraphic T is equal to
Yes.
this Latin capital T.
Yes, yes.
And now the sign of composition of or maybe I don't understand this sign, times alpha. Yes. Could you explain this? What do you mean by that? Yes.
So and okay, maybe I shouldn't have tried to phrase it into differential geometry language. I probably am crap at this. Sorry. So what I mean is I take, okay, so let's see, maybe I have it on the next slide. No, I don't. So you have these scalar fields, capital X mu. They depend on whatever your fields are. You expand them in a power series in kappa. So it gives them x0 plus kappa x1 and so on. You invert that power series, and then you evaluate your tensor field at this point, at this point. That's what I mean with the composition.
So are you using some trivialization of the tangent bundle?
Ah, yes, definitely. Yes.
Okay.
So this is always locally small tangent bundle.
So you are using locally preferred coordinate system.
Yes. So as I said, we have a background with fixed background coordinates x, and everything is formal perturbation series. Okay. So this is all well different there. So. Okay. Very good. So, well, the interpretation of this in a physical sense is how one should interpret these things is that these capital X mu, these are coordinates that depend on the configuration, on my dynamical fields, on the metric perturbation H or any other fields that I put in the theory. And calligraphic T of chi, that is the value of my tensor field T, the thing that I'm interested in, the observable that I want to look at the point where these capital X coordinates are equal, have the value chi. And then once, well, there's this x0 on the background, so that means that calligraphic T in this formal perturbation theory is actually a proper tensor field on the background. This is the interpretation. Okay. Example. Very simple example. I take a background Minkowski spacetime with preferred Cartesian coordinates x mu, and then this map x0 would just be the identity. And then I can extend this in any way I want to higher orders in kappa.
Sorry, Markus, but you realize that you are like -3 minutes behind.
Yeah, I do.
Okay.
I didn't realize that there would be so many questions. Okay, maybe then let's be very quick. I don't want to explain anything here. So these capital X mu that depend on my dynamical fields H and whatever else I can put in, since the H's are quantized and don't commute, also these capital X mu don't commute. And these are now my non-commutative coordinates. This is where I wanted to arrive at, but yeah, I didn't manage. So let's just go to the result. Here we have something. So as I said, let's go back. We take our background Minkowski spacetime with preferred Cartesian coordinates, and this x0 is just the identity map. And in general, so to higher orders, one imposes that these coordinates satisfy the, let's say, free Klein-Gordon equation, Masses Klein-Gordon equation, where, of course, where now this nabla depends on the full metric G tilde. So on the background, they are harmonic, but then there are corrections at each order in kappa. For example, at first order, the first order correction would be integral over the metric perturbation, this linear combination here, with some fundamental solution of Green's function. And now which one you take depends on the theory. So if you're in a classical theory, maybe you like the retarded Green's function. If you're in the quantum theory, what you want is the Feynman propagator. And yeah, as I said, the H that enters here in this first order construction and also at higher orders, at all higher orders, has a non-trivial commutator. So also the field dependent coordinates, they will have a non-trivial commutator. And in the free theory, it's very easy. It would just be the expectation value, because it's proportional to the identity. but in general, it will be a formal power series in this coupling kappa. And what we did is using this algebraic approach with everything that I showed you to evaluate this commutator at leading order, let's say. Let's not go through all the details. This is the result in Minkowski spacetime. So these first order corrections, which are proportional to the h, if you compute their commutator in this approach, what you get, well, there's one expression in Fourier space and one expression also in real space. And well, it has a very peculiar structure. So it's not just some constant matrix that would enter on the right-hand side, but well, so let's say the tensor structure is given by the background Minkowski metric eta. Then it's 0 outside the light cone. So this commutator also vanishes for space-like separations. That comes more or less explicitly from the fact that the commutator in the quantum theory for the metric perturbations vanishes there. And it's a constant for time-like separations, where it depends which one of the points is in the future and which one is in the past. So this is also a fully Lorentz invariant result. Yeah, being inside or outside of the light cone doesn't depend on the Lorentz transformation. And in fact, well, we know the background coordinates commute. These first order corrections don't. So if you look at, well, if you do the expansion, so the let's say the field dependent coordinates capital X, they are series and kappa. And to leading order, the commutator is the one of the first order terms, which has this form that I've given you here. So one can generalize this to, let's say, the Sitter spacetime, for example, but since I'm already out of time, we don't go there. But okay, so this is, as one can see from this, this commutator is something that doesn't need to be postulated. It really comes out of the fact that we take GR, expanded around the background, say the background is classical, the fluctuations that come from quantum gravity are small. This is what we think is a very good approximation to everyday life. And if one tries to define in the theory observables, one needs this field-dependent coordinate system, and this coordinate system is non-commutative. So non-commutativity follows from quantum gravity. It doesn't need to be postulated. Yes.
I'm sorry, just I completely failed to understand what do you mean by that being coordinate of what? In what sense are they coordinate?
So, well, they are. So here, well, I mean, coordinates. They are not coordinates in a mathematical sense. They are operators on this Hilbert space from that is obtained from this GNS construction.
So what is the physical meaning of this operator? Why they are in any sense justified to be coordinate or even using this notation X, which seems to say that it's some sort of X coordinate?
Because the physical observables of the series, or the objects that one could measure, they are.
It's not a question of what you can measure, about quantity, but what those quantities mean physically. That is the question.
Yeah, so physically, these x mu should be the actual coordinates that one could measure, because the observable coordinate of sorry,
coordinate of what?
Of some space-time event, some coincidence of whatever, some comet going to Jupiter, or so
they are not coordinates in the usual sense. They are operators.
They are operators, but their background value on the background space-time that we have in perturbative quantum gravity are the background coordinates.
They are operators of what quantity? I mean, they are operators that correspond to what kind of quantity? What is the physical meaning of that operator as a physical quantity? I just completely failed to see that.
This should be the physical coordinate that one measures. So I mean, this is now.
You just call it coordinate. Yes.
No.
No, this is it gives you a whole coordinate system. I mean, what is x mu a coordinate of the background x mu? This gives you the coordinate system in which you measure physical observables.
Tomek, what do you want to say? Okay. I thought you wanted to say something, Tomek. No?
If I could comment. So yeah, I cannot see the problem this time, okay, at this point, because they are operators whose limit when k tends to 0 becomes a flat coordinates in the Minkowski space.
Not that much is true, but then you can construct mathematical object like that. If many different mathematical object like that, that doesn't mean that they what physically that they mean. That is the question.
These are observables.
I think he answered it. He said these are coordinates of some patch of the space-time in which you make your measurement. That's how I understand it, right?
Yes, that's correct. Yes, of course. I mean, here I've given you one example.
It has to be coordinate of some geometry. What is that geometry? Your space-time is classical.
Okay. The background is classical. Yes. Okay. Of course. This is the first result which has ideas from this direction. Of course, now one needs to say what is the space-time that would correspond to that? What is a quantum space-time, a non-commutative space-time? Maybe this can be related in some way to spectral triples. I don't know. Of course, this is all open. I mean, there I don't have an answer, but the idea is that if you do this perturbative quantum gravity theory, like many people do, I mean, I'm not the only one, then as Piotr summarized, these x mu, I mean, maybe not these specific ones, but in general, these field-dependent x coordinates x mu, let's not call them coordinates, these x mu, these should correspond to the physical coordinate system in which people actually make measurements. What they are concretely depends on the concrete situation. For example, if you look in, cosmology, if you look at the sky, there's something called geodesic light cone coordinates. So there's a construction that is a bit more complicated than what I've shown you here that can be done. This is just the simplest example. But yeah, these should be the physical coordinates, or this should give you the physical coordinate system in which the measurements are made.
Okay, thank you so much. Okay, go ahead.
I think I'm running out of time, so I mean, there's a generalization to the sitter, but it becomes a lot more complicated. So let's just maybe come to the conclusions.
Conclusions, yes.
Yes. So, well, I tried to convince you, I probably failed, that to define invariant observables in perturbative quantum gravity, one needs these field-dependent coordinates. They are non-commutative. One can compute their commutator using the algebraic approach, which I presented in the beginning. And in contrast to this, let's say, Doppler, Fredenhagen, Roberts proposal, this non-commutativity is not a constant, but it's a Lorentz invariant. One can check that the standard deviation for coordinate measurements would be the Planck length. And of course, there's a lot of things that need to be done, which, well, I haven't done yet. These are quite recent results. So, of course, I mean, I would be happy to relate this also to other approaches. And there could be higher orders in kappa. What are the observational signatures of these things? And of course, the final question is, what is a non-commutative spacetime? Maybe these coordinates somehow could give some ideas what should come out somehow. Thank you very much.
Thank you so much.
Thank you.
Okay, any further questions? Adam, Andrei, Ludwig.
I have a question.
Oh no.
For a change,
Okay,
I have a question.
So Tomek for a change, okay.
Okay. So now my question is less maybe mathematical, more physical. So you started from the physical motivation for considering this field-dependent coordinate system, operator-valued operator system, to resolve this problem that for for strong gravitational fields, we have this catastrophe when something which we want to measure creates a black hole and it's hidden inside. But what we achieved is a first approximation, this perturbative beginning of this expansion, which is appropriate only for weak gravitational fields.
Of course.
So you are not solving this problem from the beginning.
No, I don't. So what one would need to do is, of course, to go to higher orders in kappa. Maybe, just take leading most important terms and see if it is possible to resum them in some way to get something non-perturbative. I totally agree. This would need to be done. It's of course complicated, it will take time, but in principle, one would need to do this. And then see what comes out.
Yeah, so I have another, maybe not question, more comment about this discussion. What are these capital X's? They are operators, which in the limits become flat coordinates.
For this example.
Yeah, but the problem is that even flat coordinates, they are not observable. Because measurement of particular flat coordinates depends on this system, or how is it called? Coordinate choice of coordinate system.
Yes.
Okay. Yes. But coordinate systems are different observers in the space-time. They are observer dependent.
Yes.
But what is independent of the observer? This geometric structure. Being flat is something which is independent of the opinion of an observer. Being so to cut this discussion about the nature of this particular X, capital X's, can you reformulate your construction in terms of this deforming of this flat structure simply?
Right. That's a very good question.
X capital mu. Say what is the non-commutative deformation of a flat geometry, Minkowskian geometry. This would cut all these discussions.
Okay, very good. Thank you very much for the input. Indeed, what one, as I said here, future work is on observational signatures. So, for example, what one could do is one could look at the Riemann tensor and compose it with these coordinates to define this relational Riemann tensor, and then see if that is zero or not. So that would be a very direct way of doing it. And then one could sort the first order, second order, whatever. And then, of course, on the background, it's zero. And then there's a correction, which might not be zero, but it might have vanished an expectation value, for example, but a certain variance, let's say. So then one would say, okay, flat space is on average flat, but it fluctuates with a certain variance. That would be, say, a next step. Yes, completely right. Thank you. That's a very good idea.
So then the next comment is in order. If you could redefine your solution to make it quantization of this flat Minkowskian geometry, the next question arises: can you rewrite Einstein equations in terms of this deformed quantum geometry? What are these equations then? Because you are using this field theory, this classical action functional, to define these effective non-commutative coordinates. But then I don't know what is happening to Einstein equations.
They will, of course, get corrections. So
Probably they are somehow hidden in this, maybe higher terms of this.
Possibly, yes, definitely. I mean, one would need to look at them. So, for example, again, one could say, take the Einstein equation, make it relationally invariant in this way, and then compute to first order, second order, whatever, what comes out. That's completely right, yes.
And this would be great.
Okay, good.
If you could reobtain Einstein equations as non-commutative geometric feature of this deformed flat Minkowskian geometry.
Okay, good. Thank you.
So deriving Einstein equations from this non-commutativity only, it would be really fascinating.
Okay. I'll put it on the list. Thank you.
You're welcome. Nice talk. Anyway,
thanks.
Forgive me my mathematical stubbornness, but
no, it's okay. I'm happy. Just wasn't expecting so much.
You know, Markus, there's this famous saying by our late friend Michael Atiyah that communication between physicists and mathematicians is very difficult, and he put it very beautifully. We are divided by the common language.
That's that's a very nice way to put it. Yeah. So people take concepts from one side without properly understanding them on the other side. Yeah.
Exactly.
And then using it to mean something else. That's probably true. Yeah. Well, I hope at least something was understood.
No questions. We are already over time, so no questions this time.
So no questions from Zoom. You guys, any more questions? Go ahead.
See you one. Thanks for the talk, first of all. Now,
nice talk.
Question. I have many unknown words. So anyway, you talk about potentially want to build spectral triples. So out of these, would you expect like the associated curvature that you would get to be related to these things that you talked about?
I know very little about spectral triples, so I'm sorry, I don't have any idea to say. For this, you would have to ask my colleague Albert Much, who knows a bit more about these things. I'm sorry.
Okay, thanks.
Okay, so let's wind it up. Let us thank our speaker again. Danke schön. It was great.
Thanks.
Okay, let me stop the recording.